Pulse echo. Bats can find their way around by sending out ultrasonic pulses, which then reflect off things around them, returning an echo, like this. Here we have a bat that sends out an ultrasonic pulse. It reflects off a stalactite and returns to the bat. By knowing the speed of sound in air, and knowing the time between sending out the pulse and receiving the echo, the bat can work out the distance to the obstacle. Of course, the bat doesn't actually do all these calculations, it is just aware of its surroundings. Dolphins use a very similar system, as does the sonar system on a ship and the radar system used by aircraft. However, the radar system uses radio waves. The same system is also used to obtain images of unborn babies. Here we have an ultrasound transmitter and receiver, which will send pulses through the womb. When the pulses reach an interface where the density of the tissue changes, some of the wave will be reflected and some will pass through, reaching another boundary where some of the wave will be reflected and some will pass through, and so on. The computer will get information something like this. It will know the intensity of the pulses detected and the time at which they are detected. So, pulse A could be the transmitted pulse. Pulse B, a reflection from a close and significant density change within the body. The reflection is from something close, as it's not taken long to return. And we've received a high intensity of echo, therefore there must be a significant density change. Pulse C here is a reflection from a more minor density change, deeper within the body. Less energy has been returned. And pulse D, a reflection from a more distant, as it's taken longer, significant density change. A large amount of energy has been returned. I'll call the time interval between A and B being detected E. And E is then the time taken for the pulse to travel from the transmitter to the interface B and back again to the transmitter. The computer uses the strength of the echo, the height here of the pulses detected, and the time of return, along with the speed of the wave within the body, to produce an image. A scan just giving this information is called an A scan for amplitude, and this can be used for accurate distance measuring. If the amplitude is converted into the brightness of an image, we obtain a two-dimensional image, which is known as a B scan or brightness scan. The resolution of the system, that is the smallest detail which can be picked up, is limited by the wavelength of the pulse. You cannot resolve anything smaller than the wavelength of the ultrasound being used. Unfortunately, the smaller the wavelength, the greater the absorption of the wave, and so a compromise is reached between resolution and penetration of the wave. The pulses need to be very short, so the outgoing pulse does not overlap with the returning pulse. This also gives a limit of resolution, and this is half the length of the pulse in use. Let's look at an example. What will be the resolution of an ultrasound pulse with a frequency of 3 MHz and pulse length 1 microsecond if its speed in soft tissue is 1500 meters per second? Well, maximum resolution could be decided by the wavelength. This is given by wavelength is equal to wave speed over frequency. Putting in the numbers gives a wavelength of this wave of 0.5 millimeter. Maximum resolution could also be half the pulse length. We know that distance is equal to speed times time. The speed of this wave 1500 meters per second, and it exists for 1 microsecond, 1 times 10 to the minus 6 seconds. So the pulse has a length of 1.5 millimeters, and half the pulse length will be 0.75 millimeters. So in this case, half the pulse length is the limiting factor to resolution, and gives a maximum resolution of 0.75 millimeters.